We are asked to determine whether the given sequence converges or diverges. We could take the limit as n goes to infinity, but let's use the squeeze theorem instead, where the middle term b subscript n is our sequence 2 to the n over n factorial. This means we need to bound the given sequence with another sequence from below and yet another sequence from above. We also need to have a hunch how our sequence behaves. And since n factorial grows faster than 2 to the n, we suspect that we are looking for sequences that go to 0. Let's begin with the lower bound. Since we know that all these terms, 2 to the n over n factorial, for all of our n larger than, say, 1, are positive, we can choose 0 as a lower sequence. To find a sequence above ours that is easy to handle, we should seek to replace n factorial in the denominator with something of a slower growth and that looks similar to the numerator. For example, n factorial is larger than 2 to the n for all n greater or equal to 4, as this table of values shows. However, this new sequence c subscript n, defined as 2 to the n over 2 to the n, is simply equal to 1, and so has a limit of 1 rather than 0 as we are seeking. So let's try 3 to the n. Indeed, n factorial is greater than 3 to the n for all n greater or equal to 7, as this table of values shows. So finally we have found two bounding sequences, one from below and one from above. Let's formally take the bounding sequences limit. The limit as n goes to infinity of 0 is simply 0. And the limit as n goes to infinity of 2 to the n over 3 to the n can be written as the limit as n goes to infinity of 2 over 3 to the n. And since 2 over 3 is positive and smaller than 1, this limit goes to 0. So, by the squeeze theorem, our sequence converges, and it converges to 0.